Good morning and welcome to today's webinar, Protecting Distribution Equipment from Electrical Hazards, sponsored by I-Gard. I'm Mike Eby, Group Editorial Director for EC&M. Before I turn the session over to our speaker today, I need to cover a few housekeeping items. First, if you have any technical difficulties during today's session, please put your question in the questions window and our technical experts will help you. We recommend that you disable any pop-up blocking software or extensions in your browser, as these can cause issues with the player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that'll follow the main presentation, but you can type your question in at any time and submit it. To do so, type it in the Ask a Question window on the side of your screen and then hit the Submit button. We'll also make available a copy of today's presentation. You can look at the Event Resources tab below the Ask a Question box and download it from there. We're also going to make sure that this recording is available on the EC&M website. That'll be posted and you'll get an email notification when that takes place. So you can share that with others. And there will also be a certificate of attendance awarded at the end of the webinar. Please note you must attend for a minimum of 50 minutes to qualify for the certificate, and it will be emailed to you within an hour of the conclusion of today's session. Now it's my pleasure to introduce today's speaker. Sergio Panetta is the VP of Engineering at I-Gard Corp. Sergio is a graduate of McMaster University, has more than 3 decades of electrical engineering experience in switchgear design, commissioning and troubleshooting, and power system protection and power system grounding. He's actively increased the awareness of electrical safety on a global front. He's a senior member of the IEEE, a member of IET, and has been awarded consulting engineering status with the PEO professional body. He's a member of several industry working groups and committees and is the author and owner of several U.S. patents related to electrical safety. So it's my pleasure to turn it over to Sergio and let him talk about the topic at hand today.
Thank you, Mike. Again, we're going to talk about protecting distribution equipment from electrical hazards. And it may not necessarily be the hazards you're commonly familiar with. So what we're going to discuss is ground fault and system grounding solutions, resistance grounding, selecting and installing neutral grounding resistors, resistor monitoring, hybrid smart high resistance grounding systems, insulation monitors, and surge suppressors. Also in there is a little bit of hybrid high resistance grounding. I don't know where the smart came from. It's just there. So ground fault and system grounding. According to the Industrial Power System Grounding Design book, which is an excellent book that's available online. If anybody wants a copy of that, let me know, and I'll certainly forward a link to where you can purchase this book. But it's a phenomenal book by Dunkey Jacobs, Shields, and St. Pierre. These guys are masters at grounding systems. They claim that up to 95% of all faults are phase-to-ground faults. 4% are phase-to-phase, 1% are three-phase faults. So a three-phase fault is very, very difficult to happen all by itself. Normally, they're man-made occurrences, forklift driving through a bus duct, somebody's taken a panel off of a piece of switchgear and it falls into the enclosure and it goes across all 3 phases. But the important thing is 95% of all faults are phase-to-ground faults. And that says something to the risk. The risk of having a fault in your system is very high when it comes to ground faults and very low when it comes to 3-phase faults. But we put a lot of emphasis in the industry about 3-phase bolted fault clearances. A phase-to-ground fault can propagate to a phase-to-phase or 3-phase fault if it is permitted to do so and you have a solidly grounded system. So we're going to discuss a little bit of ungrounded systems. So it's difficult ungrounded system has no intentional connection between the phase conductors and ground. It's very difficult to locate where a ground fault is. And we used to have a lot of these back in the 50s and early 60s. And now they're more strategically placed for certain applications. They're susceptible to transient overvoltages. If a second fault occurs, if you have a ground fault on an ungrounded system, you've basically converted it to a solidly grounded system. So the next fault is going to be a phase to ground fault as if it were a solidly grounded system. So you don't have ground fault protection according to the NEC and CEC. What there is ground fault detection. So you have to enunciate the presence of a ground fault in an ungrounded system. So if you look at the red book, the green book, the buff book, and the updated standard 3003.1, ungrounded systems where there's no intentional grounding, accumulated operating experience indicates that general purpose industry power distribution systems have overvoltages that are associated with ungrounded systems. Ungrounded systems, it's possible to have destructive transient overvoltages according to the green book, and the buff book says that you have intermittent faults. You would have subject to severe overvoltages. So the problem with an ungrounded system, and the reason why we ground in the first place, is to have no overvoltages due to overhead contact with another potential. So because you have an intermittent ground fault on an ungrounded system, there's no actual connection to ground. So you could have escalated overvoltages that occur in an ungrounded system, which is predominantly why we chose to go with a solidly grounded system after the ungrounded system to limit the overvoltages. So solidly grounded systems, if you look at the Y on the transformer, you have a solidly grounded link connecting directly to ground. The issue with unground or solidly grounded system is you have unplanned outages. So if you look at 230.95 in the National Electrical Code or 14-102 in the Canadian Electrical Code, it basically states that if you have a system that's over 150 volts to ground and greater than 1,000 amps, you must have ground fault protection. So overcurrent protection does not work when you have a ground fault. You may not necessarily have the sufficient current to trip the overcurrent device fast enough. So when you have, the Canadian Electrical Code basically says that you have to trip in under 1 second. And I think the NEC has similar verbiage that says you have to trip relatively fast because you want to stop the current flowing to prevent fires. You have high current values, severe damage. So basically, if you have a solidly grounded system, you can have anywhere from 10,000 amps to 50,000 amps flowing in that ground fault circuit. When you have a ground fault in a solidly grounded system, and when we go back to the book that came from Dunkey Jacobs, it says that because you have a ground fault in a piece of equipment, usually your ground fault is going to be inside a piece of equipment. You deteriorate the insulation around the point of the fault where it could quickly develop into a phase-to-phase fault or a three-phase fault, and then you have an arc flash event. So the red book, solidly grounded systems have the highest probability of escalating into a phase-to-phase or three-phase fault. Safety hazard exists when you have a solidly grounded system for severe arc flash, arc burning, because a ground fault can occur anywhere in your facility. And if you're working near your equipment where the ground fault occurs, you could be subject to an arc flash event. This is why people have to wear PPE when they're working on or near electrical equipment. A disadvantage of a solidly grounded system involves high magnitude of destructive arcing ground fault currents. And when you have a high magnitude of destructive arcing ground fault currents, you have the possibility of having a phase-to-phase fault. derived or derived from that single phase to ground fault. This is why we go to resistance grounding. Resistance grounding, if you remember that transformer that we had originally with a solid link from the neutral point to ground, we replaced that with a resistor. If you replace it with the resistor, your entire secondary of the transformer is protected as if it were a high resistance grounded system. So 250.36 in the NEC and 10-300 of the CEC states that if you have a resistance grounded system and you limit the fault current to a low value, in Canada it says to 4160 volts and less than 10 amps, you don't have to trip. In the US, in the NEC, it states that if you limit the fault current to a low value, less than 1000 volts, you have a high resistance grounded system and you don't have to trip. So what are the reasons that we ground with a resistor? To reduce burning and melting effects in faulted electrical equipment, to reduce mechanical stresses, to reduce electric shock hazards, to reduce arc blast or flash hazards, to reduce the momentary line voltage dip, occasionally occurrence that occurs when you have a ground fault, and to secure control of transient overvoltages while at the same time avoiding shutdowns. So where do we want to limit or protect our system with a high resistance grounded systems? For all these reasons, every location that I've been to has the benefit of employing a resistance grounded system. So we put them in petrochemical facilities where you can't tolerate an unplanned shutdown, data centers, pulp and paper facilities. In Canada, we put them a lot in banks. I've had this conversation with consultants in the States, and they said that they always, in the States, you have 51717 that basically says you have to have 2 levels of ground fault protection. The only reason to have 2 levels of ground fault protection is that if you have a ground fault and you coordinate properly, you lose much less of your electrical system. Whereas in Canada, specifically Ontario, we have high resistance grounding systems where if you have a ground fault, you don't have to trip at all. So a hospital is very, very critical that you do not have outages. And again, one resistor protects the entire secondary of the transformer or generator if it's on a generator. So how does this work? So basically, if you have a system over here, this is a 480 volt secondary. You can see our vector relationship, A to neutral, B to neutral, C to neutral is 277 volts. Phase to phase, we're looking at 480 volts. If there's no ground fault on the system, there's no current flowing through the resistor. And we have 277 volts from A to ground, B to ground, C to ground, and neutral to ground. Neutral to ground are at the same potential because there's no current flowing through the resistor. When you have a ground fault on an electrical system, that ground fault current has to return back to the source. The only way back to the source is through the resistor. So I'll show you on the next slide. When you have a ground fault, in this case, we've grounded A phase. A phase takes the bonding network all the way back to the ground plane at the source of the transformer, and then goes back to the neutral, and we complete the circuit. So the ground fault is like a switch. You close that switch, you complete the circuit, and the load of that circuit is the resistor. It's the return path for the ground fault current. So what happens when we have a ground fault on a resistance grounded system? We've now turned A phase and ground are at the same potential. We've limited that fault current to 5 amps. B phase to ground and C phase to ground are 480 volts. So as far as a load is concerned, you're still seeing 480 volts phase to phase. Between A and B, B and C, C and A, you have 480 volts. So your load continues to work. all the motors continue to work, your air conditioners continue to work, everything in your facility continues to work. But what we've done is we limited that fault current to 5 amps. We enunciate the alarm. There's another path of ground fault of current going through the capacitive coupling of your system, and that can be as high as 5 amps. But in a 480 volt system, in our experience, I've never witnessed more than 1 amp in any size transformer. So when you have a resistance ground in the system, the user, the consultant, has a choice. Do we want to go with a low resistance ground in the system or a high resistance ground in the system? So we come up with a little flow chart here. If your system is greater than 5 kV and your charging current is greater than 10 amps, you have to use a low resistance ground in the system. If your system is less than 5 kV or less than or equal to 10 amps, the charging current, you can use a high resistance ground in the system. But there's nothing really to stop you from using a high resistance ground in the system where your voltage is higher than 5 kV, as long as you trip sequentially down to a safe condition again. So there's segregation. You can trip the faulted circuit, keeping your critical processes running. So an example of a low resistance ground in the system, this one is a 2400 volts, so it's meant for a 5 kV system. We limit the fault current to 400 amps for 10 seconds. With a low resistance ground in the systems, you must have a time duration. That time duration is 5 seconds, 10 seconds, 60 seconds, extended time, or an hour. So your typical ground fault current is 25 to 400 amps. One common question that we get is so we get questions all the time and says they need a low resistance ground in the systems and they want to limit the fault current, but they don't know what value. What determines the value in a low resistance ground in the system is not the resistor, is not the distribution system, it's a protection system. So what is the minimum pickup of your ground fault protection in your system? If your minimum pickup of a ground fault is 50 amps, then certainly you can pick a 100 amp, 200 amp ground fault current on your resistor. If your minimum pickup is going to be 400 amps, you can't detect a fault of less than 400 amps, so it has to be greater than 400 amps. So your protection system dictates what size the resistor should be. So we go with high resistance ground in the system. So provides service continuity on the first ground fault. When you get a ground fault, you basically converted your high resistance ground in the system to a solidly grounded system. You've limited the fault current to less than 10 amps, so you don't have an arc flash trigger. And there's no overvoltages as associated with the ungrounded system as long as you choose the resistor to be the resistive current to be equal to or greater than the capacitive charging current. And again, on low voltage system, I've never seen a capacitive charging system less than or greater than 1 amp. And 1 amp was rare. So high resistance provides the same advantage as ungrounded systems. You don't have to trip. The voltage vectors behave the same way as an ungrounded system. However, the maximum voltage you can have phase to ground is 173% of your phase to neutral voltage, ungrounded systems. The minimal shock hazard that during a phase to ground fault, you minimize the current to 5 or 10 amps. And so there's less touch and step potential because you're limiting the fault current to 5 amps. There's no arc flash hazard as there is with the solidly grounded system, since there is a resistive ground in the system and you limit the fault current. So the Buff book, the resistance grounding, helps ensure ground current of a known magnitude, making it possible to identify the faulted feeder and isolate the faulted feeder, or more importantly, what we can do is we can locate where the fault is in that high resistance grounding system without shutting anything off and without opening any doors, exposing your personnel to hazardous voltages. We've gone out and we've looked for ground faults in facilities, and I can guarantee that I can locate a fault in any size facility in less than an hour with a high resistance grounding system without shutting down and without opening any doors. So NFPA 70E and Z462, they both say the same thing. Reducing the likelihood of exposure. This goes to risk, where the risk of having a escalating overvoltage or arc flash on a solidly grounded system is extremely high. But put a resistor in place of that solid link, and now you have a high resistance grounded system. And we've seen several documentations about how a high resistance grounded system will not escalate to a phase-to-phase fault. The book that we saw at the beginning said that it will not, 95% of all faults begin as single phase to ground faults. And the majority of all electrical faults are phase to ground type. High resistance grounding and certain impedance will ensure that your fault will not escalate to a phase-to-phase or phase-to-phase-to-phase fault. So when we look at the grounding systems that are available out there, you have an ungrounded system, solidly grounded system, and resistance grounded system. So the process continuity under ground fault, ungrounded systems do a great job. You don't have ground fault protection with an ungrounded system. You have ground fault detection, but you lose out on controlling transient overvoltages, the ability to locate the fault, limit fault current, and reduce the likelihood of an arc flash. Solidly grounded system, you have control of the overvoltages. You have to trip on the first fault. The ability to locate the fault, I get questioned about this all the time. And some people say you just look for the smoke and you find where the fault is, but you've lost the circuit. With high resistance grounded system, it seems to be the one that ticks off all the boxes. You reduce the likelihood of exposure, limit the ground fault current, you can locate where the ground fault is, you control transient overvoltages, and you have process continuity. So for selecting a neutral grounding resistor, we have to do a couple of things. So we have to look at the rated voltage. So if you have a 5 kV system, a 5 kV system is 4160 volts. So for 4160 volts, your line to neutral voltage is 2400. If you want to limit the fault current, so you have to look at the rated current at the next point. Ooh. The rated current, the maximum is 100 phase. So okay, so basically we're looking at the resistor is equal to the current you want to limit the fault to. So if you limit the fault current on a 5 kV system to 5 amp, you need a 480 ohm resistor. So 2400 divided by 5, 480 volt. If you wanted to protect a low voltage system, say 480 volts, voltage on a 480 volt is 277 volts with respect to ground. The neutral can elevate to 277 volts. We want to limit the fault current to 5 amps. You need a 55 ohm resistor. 55 ohm resistor on a 5 MVA transformer protects everything in that 5 MVA transformer, so that, remember, a ground fault current has to return back to the source. The only way back to the source is through that resistor. And as long as the total charging current, the capacitive charging current, is less than 5 amps, there's nothing wrong with putting a 5 amp resistor in there. If, however, the charging current is greater than 10 amps, you need to pick a higher rated current resistor. So this typically happens above 5,000 volts. Then you have to introduce a time. Now you're basically coordinating your protection system with the time. So if you can trip in 2 seconds, 3 seconds, remember, you want to allow some time for your system to differentiate which feeder has the fault to which circuit you want to trip. So you could play with time to coordinate your protection system so that the faulted feeder will trip. The temperature comes with the time. There's a standard in Canada, C22.2, number 295, which basically says for a time-rated duty, a duty-rated resistor, the elevated temperature is 750 degrees C above 40 degrees ambient, whereas the rest of the world has C57.32, which states that your duty rated resistor has a temperature rise of 760 degrees C above 30 degrees ambient for a duty rated resistor. For a continuously rated resistor, your temperature rise is going to be 375 over 40 ambient in Canada and 385 over 30 ambient with C57.32. So we go for the charging current again. Typically what happens is you can determine what charging current is on your system doing several things. You can measure the current at the ground fault and subtract the resistor, vectorially subtract the current going back through the resistor. And you can figure it out with this relationship. So the fault current at this point, at point A, at A phase, is equal to I-R squared, which is the current going through the resistor, plus 3IC0, which is your charging current squared. So IF can be the maximum of 7.07 amps if you limit your fault current to 5 amps and your charging current is 5 amps. And the maximum fault current at the point of fault is going to be 7.07 amps. So again, C57.32, 2020, resistance NGR should be, the change in resistance is suggested that should not change by more than 67%. Now, 67% I think is a lot. In Canada, with the CEC, it basically says your resistance should not change by more than about 25%. Because of this is the formula to determine the change in resistance based on the material you use for the resistor. So alpha is the temperature coefficient of resistance. The final temperature, the final resistance of your resistor is going to be equal to your initial resistor plus the 1 plus alpha, the temperature coefficient of resistance, times the change in temperature. I'll give you a better example of that. That's confusing. I'm sorry. So let's look at a low resistance ground in this system. 2400 volt, 400 amp for a 10-second resistor. Your temperature is 760 degrees C above ambient. So we're using C57.32 here. So the resistance ends up being 6 ohms. The temperature coefficient of these 4 types of steel, which are commonly used to make resistors, is 0.00092 for 304, 0.00146 for 430, 0.000358, and 0.000241 for 1JR. Now, these all look like relatively low numbers. So when we get specifications that say the resistor should have a low temperature coefficient of resistivity or resistance, these are all low. But let's compare these low values to each other. So at the end of 790 degrees C, so a 760 degrees C temperature change, your resistance from a 6 ohm resistor changes to 10.2 ohms for 304. It more than doubles for 430, and your current changes correspondingly from 400 amps to 234 amps, from 400 amps to 189 amps for 430. This is the resistance element that we use. So we have a 7.1 increase, or 18% increase in resistance to 7.01, which decreases the current by 15.4%. For a high resistance ground in the system, 5 amp, 277 volts, 55.4 ohms, same materials, same temperature coefficient of resistance, 35% increase in resistance, 56% increase of resistance. The only difference here is we've lowered the temperature for this formula here. Theta 2 minus theta 1 is 385 as opposed to 760. So we have less temperature resistance change. So these two elements violate the rules in C57.32 and C295 CSA. So if you have a resistance grounded system and you have a Y-connected source, easiest thing to do is just put a resistor between the neutral point and ground, and you want to limit the fault current. Remember, all fault currents have to return back to the neutral. If you don't have a neutral, or what I like to do is use this on multiple sources, put a zigzag transformer with a resistor. Same resistor here as here, based on the time content. If you have a time-rated resistor, you may have to decrease the resistance because the zigzag transformer is going to have some impedance in it as well. So if the zigzag transformer has impedance, you must decrease the impedance of the resistor to limit the fault current back to the desired current. Conversely, if you don't want to use a zigzag transformer, you can use a Y-grounded delta or a Y-grounded open corner delta. And if you're as old as I am, you'll know what a Y-grounded open corner delta is. So we get into resistor monitoring. So in Canada, under CSA M421 for the past 30 years, we have had to have resistor monitoring in the mining sector, and it's been recently adopted into the Canadian Electrical Code, where every resistance grounding system has to have the resistor monitored to make sure that it's in the circuit, because if it's not in the circuit, we can quickly change the system to a solidly grounded system or an ungrounded system if something happens to the resistor, and we can discuss that. The integrity of the impedance grounded device shall be monitored to control the as required by 14, table 17. So table 17 basically says, if you have a high resistance grounded system or low resistance grounded systems, you must have to do one of these things. And the only thing that really changes is a loss of continuity. So if your resistor becomes open circuited, you have to do something, either alarm or alarm within 48 hours. And the difference between these two systems, these two clauses, is whether you have the ability to detect a ground fault on an ungrounded system or not. And you'll get the slide so you can see this. So basically we're looking at a short circuit in the neutral or an open circuit in the neutral, right? So we monitor that integrity. And if you notice, we have to have a second connection all the way back to the source neutral, because I have to verify this continuity from the transformer neutral to the resistor. So high resistance grounding system is specifically designed for medium voltage bus connected generators. And here's an example of a medium voltage bus connected generator. So we have 400 amp, 10 seconds, medium voltage. So you're looking at 13.8 kV generators or whatever. You have a ground fault on your system. It's a through fault. Your protection device clears that fault and we're good. Now you have a fault internally to the generator winding, the stator winding. You open up the ground fault protection. Have you cleared the source from the load? Well, you did for some of it, but you didn't for all of it. So the contribution of this 400 amp resistor and this 400 amp resistor from generator one in the utility is shown here as you're causing 2,200 watt seconds of energy. If there were 400 amp resistors, if there are 800 amp resistors, you're up over 6,000. So the formula is there, it's hard to see. Now, what we haven't done is we haven't cleared the source from the resistor. And this is the amount of damage that occurs to the generator after the breaker is opened. So we've, as protection engineers, the only thing we can do is open the breaker, but we haven't protected the fault from the source. So if we do everything together, we end up with this. 100 milliseconds, we've cleared that fault for differential and 5-cycle breakers. Internal fault, the cyan, and the purple one is the total heat caused. Why this is important is because we have two manufacturers of alternators here, and they state that if stator fault winding damage curve, they can handle, this one can handle 110 amps for less than 500 milliseconds. This one over here, acceptable damage, considerable damage, extensive damage. Extensive damage starts at 75 amps. So IEEE got together and a lot of the brilliant minds came together with a hybrid high resistance grounding system. So what happens is you get a ground fault. You simultaneously have a low resistance grounding system and a high resistance grounding system connected to the neutral of that generator. When you have a differential fault, the differential picks up, you open the circuit breaker for the generator and the low resistance grounding system, allow that generator to coast down with a 10 amp fault on it. So this is how it looks with a 10 amp fault on it. We've minimized the damage to 3,000 watt seconds due to the other two resistors. Conversely, we can just put a zigzag transformer on the bus. We spoke about this earlier when we have multiple sources. So when you have an internal fault, this resistor on the zigzag transformer takes care of all through faults and provides enough ground return current to trip the overcurrent protective device. But if the circuit breaker opens for the generator, we limit the fault current to 10 amps and seconds, and now we're down to 900. Why this is important is because there's been many examples, incidences where generators have failed and insurance companies don't want to pay the users because, let's face it, they're insurance companies. They don't want to pay. So you help protect the generator with a hybrid grounding system and minimize the damage. So it goes from a local repair job as opposed to a total rehaul of the generator. So we're also coming up with motor insulation deterioration or motor protection relays, looking at the insulation of a motor before you turn it on. So there's continuous deterioration of a motor, there's stress factors, moisture, consequences of neglect. All these, so when you shut off a motor, it's been running for a long time, it's hot, it's going to accumulate dust, it's going to accumulate moisture. Before you turn it back on, you want to make sure that the motor has good insulation with respect to ground before you turn it back on, and that's what this insulation monitor does. So we look at we inject the voltage onto the bus and measure how much current is on the bus. So we're looking at a couple of things. We're looking at the capacitive charging current, the absorption current, and the conduction current. So we're looking at with this curve to ensure that the insulation resistance coming soon, we inject for medium voltage 5,000 volts, and the insulation monitor can produce 5,000 volts and test enable insurance monitoring and testing up to 34 kV. And what we're looking at is we're looking at the absorption ratio and the priority index, and we have to make sure that these things are held within tolerances. So we're looking at deterioration over time, repeatability of the test. Every time you shut down the motor, we were going to do the absorption test, dielectric absorption test, 60, 30 seconds or 15 or 30, 15 seconds, and the 10 1-minute ratio of the polarization index to indicate that motor is within tolerance or not, or the insulation level of that tolerance or not. And again, there's many things that high humidity, dust, moisture, corrosive environments, and well, even man-made man-made obstacles. You know, sometimes you can leave the ground on if you're doing some work. So the other thing we've introduced is the surge suppressors. So transient surge causes, okay, there's pre-strike of contactors. Try to look at it like this. If over the past 10 years, we've tried to make transformers more efficient. To make them more efficient, there's less losses, and because there's less losses, there's less impedance in the system. An impedance in the system is like a shock absorber. If you remove the impedance, you have no shock absorbers. Every time you switch a circuit on and off, you may have insulation damage, surges that occur because there's no shock absorber there to protect you. So we can have surge arresters, which provides minimal protection for surges, surge capacitors, surge RC stubbers, or surge stubbers. The difference is this one, surge arrestor, requires a long-term overvoltage. You have to exceed the MCOV before it operates. With the surge suppressor, it reacts specifically to very fast transients and shorts to ground. So these particular devices are range from 400 volts to 40 kV. And we look at different types of surges. So these are some of the surges that we look at. Normal operation, when you switch the circuit breaker on or off, you have these traveling waves that can multiply when they hit the reflective point and come back to cause this kind of damage. What we're trying to do is minimize this damage that occur on a transformer or a generator. And so we're trying to protect this. So the surge gets shorted to ground, and we protect the system with that way. So the spike clamping is a beautiful thing. Fans, pumps, compressors, mills, all these things we can protect with a surge suppressor. But more importantly, I'm working on a job now where some external capacitor switching can cause a surge in the line, so we would shunt the surge to ground. And with that, are there any questions?
All right. Yes, so we got quite a number of questions in the queue, Sergio. So appreciate the audience interacting with us today and submitting some questions to get a little bit of discussion going following this presentation. I'll jump into a few of them now, and you can provide answers, Sergio. So one question that came in, I'm not sure which slide this person's referring to, but they said the slide showed fault current, but when you narrated, you mentioned charging current. So their question is less than 10 amps or greater than 10 amps for charging current or fault current?
Okay. Sometimes my tongue gets ahead of me. I apologize for that. I think you're looking at this slide here, and when you have a fault, okay, when there is no fault on the system, you're going to have charging current. Charging current is basically the amount of current flowing through the capacitor to ground. All your conductors in your facility act like capacitors. So when there's no fault on your system, these capacitors are going to allow current to flow from your system to ground. The only way they're going to go back is through the other distributed capacitance, because there's going to be 480 volts. None of the current from your charging current is going to go back through the resistor, even if you have unbalanced loads. So you could have a lot of unbalanced loads here, but the only current that's going to flow back through the resistor is a ground fault current. So this is very important to understand. So you could have 480 volt heaters connected to A and B, B and C, and C and A. If they're unbalanced, they're not going to produce any current flowing through the resistor here. The charging current is the current that goes from A phase through the capacitance to ground, through ground to all the other distributed capacitance that are on B phase or C phase and return back to the source. That's the only way they can return back to their source. But this ground, I've shown it here as a single point to ground symbol. In fact, this ground goes through your entire factory, your entire facility with the bonding network. These are all one ground. I hope that answers your question.
Yeah, I think so. I appreciate that clarification. All right. John has a question for you. What range have you seen for leakage current in facilities greater than 5 megavolt amperes?
Low voltage, again, with low voltage, it's going to be relatively small. The highest capacitive current, not leakage current, but capacitive current I've seen on a system that had in excess of 50 generators at 13.8 kV, when we did the math and we calculated, was over 500 amps. But it was like over 50 generators connected to one system with a lot of ties. But for low voltage, we're relatively going to have a small current.
All right. Appreciate that answer. Emmanuel asks, are there issues on medium voltage systems, they reference 13.2 kV, with NGR and underground concentric shielded cables, with the shields grounded on multiple locations, such as splices, load break switches, including the low voltage transformer?
Well, the concentric neutral is going to form a path for the ground current to return back to the source. So if the concentric neutrals are grounded at several locations, then the ground fault current will take the path of the concentric neutrals to get back to the source and go through the resistor. The only difficulty I could see now, the only difficulty might be if the fault current is only going back through one phase. But if you're saying all the concentric neutrals are tied together to ground, then there's multiple sources for that current to take back to the source. You heard the expression that current takes the path of least resistance. It's not true. Current takes every single path that's available to it. And the more grounds you have, the more paths that current has to get back to the source. Here, all these paths go back to the source. So you have an entire network here. Now your concentric neutral typically is going to be 1/3 the current carrying capacity of your conductor. So if you have multiple and you're on a 13.2 kV system, you might limit your fault current to 400 amps. You're looking at a less current going back through each concentric neutral. So I don't see a huge issue.
All right. Our next question comes in from Chris, and he says, in your NGR example, would it be wise to check for harmonics before the installation? And the reason he asks is, he says he's seen them melt down due to harmonics just below IEEE 519.
The resistor meltdown?
He doesn't specifically state that.
Yeah. The only we've had multiple facilities that use neutral high resistance grounding when they had massive amounts of variable frequency drives. Now, the one thing you do have to check for is that the variable frequency drives are compatible with the resistance grounded systems. And there are some manufacturers that use drives that are can be made modified to the high resistance grounded system. So we've never had meltdowns of the resistor with harmonics, but we've seen some instances where the drive itself is not compatible, mainly because on the front end over here, if you notice that the MOVs that they put on the front end of the drives aren't really rated for 480 volts from phase to ground. So you always have to check your TVSS is suitable for use with the resistance grounded system, and your variable frequency drives are suitable for use with your resistance grounded system. The other thing you have to check for is that with the resistor monitoring, not all resistor monitoring devices that are on the market can accommodate YY connected PTs that are downstream from the transformer. So they may not necessarily work. And they may have difficulty with multiple sources. So I would, if I didn't answer your question, please email me and I'll give you a better answer. But I'm not sure what burned down.
All right, Sergio, Scott submitted this question: for parallel generators with neutral resistors grounded individually at the generator, harmonics can still be an issue. Can the addition of a grounded zigzag transformer help with this?
Yes. I have a whole other presentation for this. But if you look at this, you have a high impedance here. So this is a very important topic when you have specifically generators of different pitches, because there's a lot of circulating currents in this system, and you could have a lot of currents. I have a whole different presentation on that, and we can save that for a later date. But having a high impedance on the neutral point of these generators minimizes the harmonics and the voltages, or not minimizes the harmonics, but minimizes the current of the harmonics because of the high impedance of the resistor with this scheme. If you have solidly grounded systems, you're going to have a lot of circulating currents. But with multiple medium voltage generators tied together, think you may, this is going to be, you're going to have 1,600 ohms on a 13.8 kV system if you limit the fault current to 10 amps. 800 ohms here and 800 ohms here. So that's a lot of current limiting resistors we have in there. Thank you.
Paul noticed on one of your slides, I believe, that it said insulation monitoring relay coming soon. He's wondering when that might be available.
Well, get in line behind my boss. How's that? It should be ready within a month or 6 weeks. It should be, mind you, I got to wait for UL too, so it's going to take a little bit of time. And where we use a lot of these things is we already have one that's available now. The difference is the one that we have available now only puts on 12 volts DC on the bus. The one that we're coming out with has 250, 500, 2,500, and 5,000 volts DC that you can put on the bus to measure the absorption and priority index. But if you need one right now and you're good with 12 volts, it's available right now.
Sounds good. Jacob wants to know, since there are many benefits of a resistance grounded system, are there reasons or instances when you wouldn't want to use a resistive grounded system? I think you pointed it out earlier, maybe, but it might be worth reviewing.
Yes. One of the disadvantages in using the resistance grounded system is that you do not have phase to neutral loads. So if you have a system, a shopping center, shall we say, and all the lighting is 277 volts, it's not practical to put a resistance grounding system in there. What we do sometimes is put the mechanical loads on a resistance grounded system, so have an isolation transformer to take care of the comfort loads, shall we say, of air conditioner and heating, because you don't want, when you have a solidly grounded system and you have a distributed neutral, you have a lot of line to neutral loads. You could put in an isolation transformer to handle only the mechanical load. So even if you have a ground fault on the solidly grounded system, the mechanical loads will continue to work. And conversely, there's a lot of loads right now that are not 277 volts, but a lot of the LED lighting are coming out with 240, 480 volt LEDs. Everything can use a resistance grounded system. So it depends on whether you're going to use that neutral or not. For 12208, you have a distributed neutral. I wouldn't put in a resistance grounded system.
All right, thanks. Let's see, Dexter asks, what is the best way to reduce ground fault current in a distributed generation application with multiple generators without adding an NGR to all the generators?
Without adding an NGR to all the generators. To minimize ground fault current? Well, the only way to minimize ground fault current is to put an impedance in the return path. So it's either going to be a resistor or an inductor. So I don't know how you're going to minimize ground fault current. Was that what you wanted to minimize, the ground fault current?
Yes.
And it's not a good idea to leave it ungrounded. So there's no way without using a resistor or some kind of an impedance to limit the fault current.
Right. All right. Based on the surge protection image that you had on one of the slides, Jacob's interested, are you stating that we should add surge protection at the motor to protect the motor installation? Typically, he says, I see surge protection installed at the distribution equipment, not at the load.
Yeah, we can put it at the load as well. If you put it at the load, what happens is it sort of captures, if you don't have access to the source, you have to put it on the load. So with this particular surge suppressor, we put it at the load because we had access to it there, and we would minimize the reflection point at that point and protect the transformer and the motor as well.
All right, let's see. Johan says, could you elaborate a bit more on why the system charging current will only go through distributed capacitance, but not through the NGR?
Sure. Let me find the right page. So, healthy system, distributed capacitance, all these phases are 120 degrees apart from each other. So the only thing that's going to happen here is you're going to add up the current from A phase here, B phase, and C phase, and only the imbalance of the distributed network will come, well, it won't go through here because we're not changing the current. They're going to add up to zero because whatever load comes in here is going to go back the other two phases. This distributed current does not return back on the neutral because there's no path to the neutral. You have 0 volts at the neutral, you have 0 volts at ground, you have 277 volts. So there's 480 volts between A to B, B to C, and C to A. That's where the current is going to go. Does that make, if that doesn't make sense, please email me and I'll be happy to share some more insight.
All right, looks like we've got time maybe for one more question. Let's see. By the way, lots of positive comments on the presentation, and people are looking for your email address, Sergio, as a
Yeah,
side
give me
note.
my email. spanetta@i-gard.com. No A in guard. No, sorry, no U in guard. I apologize. And
All right.
did we, you know what, with the slide, we'll email me and I'll send you a link to that book for anybody that wants that book. We don't sell it. It's sold by a family member, I believe, of Dunky Jacobs.
All right. All right. Here's the last question for you, then we'll wrap things up. When would you use a resistor versus a reactor for neutral grounding?
Okay, that's a great question. And I get this from my salespeople all the time. The difference between a resistor and a reactor, there's a couple of things. Reactors are really good when it comes to high current. So you don't want to limit the fault current to a couple of thousand amps, you know, if you're interfacing with a utility. And if you want to observe the X over R ratio of your system. So if you have to limit the over voltages, you may be better off using a reactor at high voltage so you don't get the high magnitude of voltages on the unfaulted phases by having a great deal of current flowing through the reactor. You're going to trip, but you're not going to get the over voltages. So you'll save a lot of the lightning arresters on your system. So, because remember, what happens is, if we go back to this slide over here, when you get a ground fault, the unfaulted phases are going to elevate the full line-to-line potential. But if you have a lot of current flowing through your resistor or reactor, you're not going to get this over voltage that occurs on the unfaulted phases. So that's the main difference between a resistor and a reactor. A reactor will limit the over voltages because you've got so much current flowing through it. And the resistor, if you have a lot of current flowing through it, you're going to get a higher voltages because of the X over R ratio.
Okay. Well, Sergio, thanks again for a fantastic presentation. We had a great audience, a lot of good questions. There were some that did not get answered. Maybe Sergio can follow up on some of those with you. He'll have contact information for you. And on behalf of ECNM, I'd like to thank I-Gard as well for making today's event possible. And we appreciate everybody joining us today, and hopefully you'll see us again soon with another webinar. Have a great afternoon, everyone, and be safe out there.